Well, welcome to chapter 16, which is on acids and bases. It is actually, in the beginning, we'll talk just about acids and bases, but it's really more about acid-base equilibria. Now that we've talked about equilibrium, um, we can apply equilibrium principles to acids and bases. These first few sections are mostly just about definitions and behaviors of acids and bases, but I do bring the concept of equilibrium constants into this video just a little bit. By the way, it's like day 3 or 5 or 20, I don't know, that I've been waiting for John Stewart and Will to send me a video of somebody playing video games to the tune of Africa by Toto, I believe, with the dancing chunguses across the screen. I believe that was the deal. Anyway, hopefully that'll turn up soon. Okay, so we talked about this in chapter 4. Svante Arrhenius, who was a Swedish chemist, he had developed definitions of acids and bases. And an acid is something that when you dissolve it in water is going to increase the concentration of hydrogen ions. And a base is something that when you dissolve it in water is going to increase the concentration of hydroxide ions. And that is a useful definition in a lot of contexts, but it really only allows us to think about acids and bases in terms of their reactions with water and not really in terms of their reactions with each other. And so we need some better definitions to allow us to do that second thing. And so the more common definition of acids and bases that we use in terms of reaction is what's called the Bronsted-Lowry, or often just shortened to the Bronsted definition. And so a Bronsted acid is a proton donor. And let's remember from chapter 4 that a hydrogen ion, an H plus ion, simply consists of a proton, because when you take an H plus atom, which has one proton and one electron, and strip the electron off to give it a +1 charge, you're just left with a proton. So we use the term proton in acid-base chemistry to designate an H plus ion. It doesn't mean we are adding or removing protons to the nuclei of heavier elements. It simply means adding or removing an H plus ion. And so we use H plus and proton interchangeably. In order for a thing to be a Bronsted-Lowry acid, it has to contain an ionizable hydrogen atom. Well, what do we mean by ionizable? Well, in theory, actually, any compound or ion that contains a hydrogen atom could be an acid. It simply has to do, in the end, with what the magnitude of the equilibrium constant is. And I'll talk about that a little bit more in just a second. So there are certain things with hydrogen atoms that we consider acids. And there are certain things with hydrogen atoms that we do not consider acids. But in fact, anything with a hydrogen atom can, in theory, be thought of as an acid. A base, instead of being a proton donor, is going to be a proton acceptor. In order for a thing to be a base, it either has to possess a negative charge to accept that H plus, or a non-bonding pair of electrons. And because we take some chapters out of order, and so we're talking about acids and bases before we're talking about bonding and Lewis structures, I'm really going to stay away for the most part about talking about non-bonding electron pairs. Okay, so what are some examples of acids? Well, hydrochloric acid is a strong acid, as you'll recall from chapter 4. It ionizes completely in water. Acetic acid, whose formula I've written out here, is a weak acid. I've intentionally made this hydrogen red to say that this is the hydrogen atom of acetic acid. That's actually the ionizable hydrogen. Okay, that's a weak acid. It ionizes only partially in water. And then methane, which we really wouldn't consider an acid at all, I've listed here because it does contain hydrogen atoms. And so what does that mean with regard to its ability or inability to be an acid? Well, now that we've talked about equilibrium, you might imagine that these things, the extent to which they behave as acids is governed by equilibrium constants. And so for hydrogen chloride, it turns out that the K for the ionization reaction is very high. It's about 100,000. And so when you put hydrogen chloride into water, it ionizes completely because it's got a huge K value, much greater than 1. You might imagine for acetic acid, because it only ionizes partially, that it's got a K value less than 1, and it does. The value of K for the ionization of acetic acid is 2 times 10 to the minus fifth, and so it mostly remains intact. We can actually measure a equilibrium constant for the ionization of methane. It is 1 times 10 to the minus 60th, which is why you can appreciate that though in theory it is an acid, it is for all intents and purposes a completely negligible acid, because that's such a vast, infinitesimally small number that the reaction simply doesn't happen. What are some reactions of bases? Well, hydroxide would be an obvious example of a base. We've talked about that a lot. Fluoride is another example of a base because it has a negative charge, therefore it could accept an H+. Ammonia is a base that we'll talk about a fair amount. It does not have a negative charge. Let's think about how each of these things accepts a proton. In the case of hydroxide, hydroxide can accept a proton to give you water. Fluoride could accept a proton to give you HF, hydrofluoric acid. And then this is the only foray into Lewis structures that we're going to do for the most part in this chapter. But ammonia, which has this structure shown in which a nitrogen is bonded to 3 hydrogens, but then a non-bonding pair of electrons, that non-bonding pair can be used to accept an H+ and form a bond to give you the ammonium ion. Now that leads us into, well, I'm sorry, before that, let me just talk about one more thing, which is what are called amphoteric species. And an amphoteric substance simply means a substance that could act as either an acid or a base. So what would be some examples of that? Well, the bicarbonate ion, remember baking soda is sodium bicarbonate. Because this has a negative charge, it can be a base and accept a hydrogen. Because it has a hydrogen atom on it, it could be an acid and donate a hydrogen. So bicarbonate is an example. Bisulfate is another example. Once again, it has a negative charge to accept an H+. It has a hydrogen atom to donate an H+. Water, although it doesn't have a negative charge, does, like ammonia, has non-bonding electrons. So it can both donate a proton to form the hydroxide ion, or it can accept a proton to form the hydronium ion. So each of these can either donate or accept a proton. Now, if this conversation about what happens when a thing donates or accepts a proton and what it forms leads into the conversation about conjugate acids and bases. And so conjugate really is a term that describes the relationship of certain acids and bases to each other. You could talk about, let me just try and give sort of a human example of this. If we talk about Mr. Shaw, okay, Mr. Shaw is a man. Mr. Shaw is also a husband. He is Mr. Shaw, the man, to everyone, but he is only the husband to one person. Or we can talk about Ms. Garrett, the woman. She is Ms. Garrett to everyone, but she is only a wife to one person. And so that is something to keep in mind when we start talking about conjugate acids and bases. A conjugate, because they come in pairs. So if you are an acid, you have a conjugate base. If you are a base, you have a conjugate acid, and they come in pairs. The identity of your conjugate partner is very specific to your formula, and we'll talk about this in just a second. So, but more generally, a conjugate acid-base pair are two species that differ from each other only by the absence or presence of a proton or an H+. So when you remove an H+ from an acid, you form its conjugate base. When you add an H+ to a base, you form its conjugate acid. What's important to understand is there's not a difference. There's not some things that are acids and other things that are conjugate acids, and there's not certain things that are bases and other things that are conjugate bases. Every acid is the conjugate acid of something, and every base is the conjugate base of something. And we'll, again, get into descriptions of how to figure that out in just a minute. And any acid-base reaction that we can write, any Bronsted acid-base reaction that we can write is going to consist of two conjugate pairs. So let's see what we mean by that. And so let's take this example of the reaction of nitrous acid with water to give the nitrite ion plus the hydronium ion. And so any proton transfer reaction that we write like this, we can look at the reactants and classify one of them as an acid and one of them as a base. In this case, the nitrous acid is the acid because it is donating an H plus to go over and become nitrite. Water is the base because it is accepting an H plus from nitrous acid to go over and form hydronium. Well, because we've written this as an equilibrium, we can also identify the acid and the base for the reverse reaction. And this is actually a reaction whose K value is much less than 1. And so it's actually the reverse reaction that's favored at equilibrium. If we go over here and say, what is donating a proton to go over to the other side? It's the H3O plus. It's donating a proton to form water. Nitrite is accepting a proton to go over here and form nitrous acid. And so we can look at that and identify an acid and a base on both sides. Now remember, we defined a conjugate acid-base pair as being two species that differ only by the presence or absence of an H plus. And so we can say, hey, we've actually got two conjugate pairs here, nitrous acid and nitrite. What's the difference between nitrous acid and nitrite? It's an H plus. The acid has it, the base doesn't. If I lose the H plus, I become the base. If I add the H plus, I become the acid. This is a conjugate pair. Similarly, water and hydronium are a conjugate pair. If I add an H plus to water, it becomes hydronium. If I remove an H plus from hydronium, it becomes water. These two species differ only by the absence or presence of an H plus. So any Bronsted acid-base reaction is going to have is going to contain two conjugate pairs. The key thing to understand is that one member of each pair is always going to be on either side of the arrow. Nitrous acid, nitrite, water, hydronium. It's never the case that these two on the reactant side are going to be a conjugate pair, or the two on the product side are going to be a conjugate pair. The pair is always going to take one partner from one side of the reaction and one partner from the other side of the reaction. So given that that's the case, let's go back to those amphoteric species because this makes a great problem. And I'm going to give you, because these can go in either direction, then each one of these has a conjugate acid and each one of these has a conjugate base. So the question to you is, take a look at these three species and see if you can write down what the conjugate acid of each of these three species is. Okay, so what is the conjugate acid of each? What is the conjugate base of each? Well, here are the conjugate acids. Remember, to go from a base to its conjugate acid, you add an H plus. When I add an H plus to bicarbonate, I get carbonic acid. When I add an H plus to bisulfate, I get sulfuric acid. When I add an H plus to water, I get hydronium. So each of these is the conjugate acid of the corresponding species in the middle. What about the identity of the conjugate base of each? Well, to get from an acid to its conjugate base, you remove an H plus. And so the conjugate base of bicarbonate is carbonate, because that's what you get when you remove an H plus. The conjugate base of bisulfate is sulfate. That's what you get when you remove the H plus. Conjugate base of water is hydroxide. That's what you get when you remove an H plus from water. We've kind of touched on this already, but let's just quickly say what happens when an acid dissolves in water. Water is going to act as the base. The acid is going to act as the acid, and you're going to get an acid base. You're going to get a proton transfer reaction. And so there's no such thing as an H plus just floating around in water by itself. It always is going to associate with the water molecule. And so when we put hydrogen chloride into water, we get a Bronsted acid-base reaction. The HCl donates a proton to water to make hydronium. Again, the conjugate pairs here are HCl and chloride. They differ from each other by the absence or presence of the H plus. The other conjugate pair is water and hydronium. They differ from each other by the absence or presence of the H plus. This is a strong acid, and so this is a reaction that very strongly favors products. And so, in fact, this has been written not with an equilibrium arrow because the K value for this is so large that we just consider it as having gone completely to. Well, we can think about acids and bases in terms of their strength. And although it's convenient to bin them into things like strong acid or weak acid or negligible acid, it turns out that they actually all lie on a continuum. And now that we've talked about equilibrium, you can appreciate that's because they all have slightly different equilibrium constants for their ionization, and therefore we can essentially rank order acids by strength. The larger the equilibrium constant, the more thorough the ionization, the stronger it is. The smaller the equilibrium constant, the less it ionizes, the weaker it is. And you can see, back to that other slide that we talked about the three acids, strong acid, hydrochloric acid, weak acid, acetic acid, negligible acid, methane. It's such a negligible acid that it essentially doesn't ionize at all. It's a really important category to these categories, though, are very useful to remember. And over on each side, we've written over on the right-hand side, we've listed the conjugate base of each one of these acids. So the conjugate base of hydrochloric acid is chloride. The conjugate base of nitric acid is nitrate. Conjugate base of HF is fluoride. Conjugate base of ammonium is ammonia. Conjugate base of water is hydroxide. You can appreciate that there's sort of a reciprocal relationship between the strength of an acid and the strength of its conjugate base. The stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. And this makes sense at two levels. If K is really large for the forward reaction, making this a strong acid, then K is going to be really, really tiny for the reverse reaction, making chloride a very weak base. The other way to think about this is that if HCl is really, really good at giving up its proton and doesn't want to have it, then you can appreciate that that makes chloride a very weak base, because if HCl doesn't want its proton, that means that chloride is going to have a very difficult time gaining any. And so this is very nicely, the way they've got this set up is very nice. The conjugate acids, the conjugate bases of strong acids are all negligible. In other words, they essentially don't add any hydroxide to solution at all when you put them into water. The conjugate bases of weak acids are weak bases. If you put the weak acids into water, they will generate a little bit of H+. If you put the weak bases into water, they will generate a little bit of hydroxide. Negligible acids, their conjugate bases are strong, because if these don't want to give up hydrogens at all, then their conjugate bases are going to be really eager to grab hydrogens to go back to being these things that are stable and happy. And so anything that's a strong base, which would be from hydroxide on down, is something that when you put it into water is going to give you a stoichiometrically equivalent amount of hydroxide. So anytime you have, and so we can use these to talk about which side the equilibrium is going to lie on for an acid-base reaction. Because in any acid-base reaction, the equilibrium is going to favor the conversion of the stronger acid and stronger base into the weaker acid and the weaker base. Let's just give a really obvious example of this, and that would be the reaction of hydrochloric acid with water, which we talked about before. Hydrochloric acid is a strong acid. Water is essentially a weak to negligible base. So water is a weak base. And so that's going to form hydronium ion plus chloride. If we think about this, water, although being a weak base, is a stronger base than chloride. Hydrochloric acid is a stronger acid than hydronium. Let's just go back to that table. Hydrochloric acid is a stronger acid than hydronium. Water is a strong, even though not a strong base at all, is nevertheless stronger than chloride. And so you're going to favor the reaction of the stronger acid and the stronger base to form the weaker acid and the weaker base. So let's now take this and use an example that may be just a little bit less clear, and that would be the reaction of acetic acid with water. So if we go, and so here's the way to think about this. Using this rule, in any acid-base reaction, the equilibrium will favor the conversion of the stronger acid and the stronger base into the weaker acid and the weaker base. So the way to resolve this, which side is going to be favored at equilibrium here? The first thing to do is to go through and identify your acids and bases. In the forward reaction, acetic acid is the acid, water is the base. In the reverse reaction, hydronium is the acid, acetate is the base. Okay, now we compare our two acids. Which is the stronger acid? Well, if you went back and looked at that table, you can find it in your book. Hydronium is a stronger acid than acetic acid, and therefore hydronium is the stronger acid, acetic acid is the weaker acid. Remember, the weaker the acid, the stronger the conjugate base, and vice versa. So because acetic acid is the weaker acid, acetate is the stronger base, kind of animated these out of order, because hydronium is the stronger acid, water is the weaker base. And so we said that the reaction is going to favor the conversion of the two stronger species into the two weaker species, and therefore this reaction is going to favor reactants. Well, this video has gone on long enough, and so I will save the description of the P function to the next one. So what would you expect in terms of a QOD? Probably things around relative identifying conjugate partners. So identifying conjugate partners would be a good thing to talk about. And then probably a little bit of what we've just been talking about using a table or data given to you to identify in a reaction what's the weak base, what's the weaker base, stronger base, weaker acid, stronger acid. And so please try some of the suggested problems, and we'll see you in class for the QOD. Thanks.